Here's problem number 7 on the sample test. A current loop in the shape of an equilateral triangle of side length 10 centimeters is placed in a uniform magnetic field 0.8 Tesla. When I is equal to 1.2 amps, what is the magnitude of the maximum torque on the loop? Alright, we're going to have to find the area vector for this, and we need to find the area that it represents. That for an equilateral triangle, that's 1/2 the base times the height. So in this case, the height is equal to a sine 60 degrees for equilateral triangle, and that would be equal to 0.1 sine 60 or 0.0866 meters. The area is going to be 1/2 the base times this height, so that's going to be 1/2 times 0.1 times 0.0866, and that is equal to 4.33 times 10 to the minus 3 meters squared. Now the direction of that area vector is going to be given by the right-hand rule. If you curl your fingers in the direction of the current going around the loop, your thumb points in the direction of the vector, area vector. In this case, the area vector would be coming out of the page towards you as you curl your fingers around counterclockwise around this loop. So the area vector is coming out of the page towards you, and hence there's going to be a 90-degree angle between the area vector and the magnetic field vector B. Good to know. Alright, so our torque is equal to the number of turns, the magnetic moment, which is current times the area vector, crossed with the magnetic field. And the magnitude of this torque would be equal to N I A B sine theta, I'm going to say phi in this case, where phi is the angle between the area vector A and the magnetic field B, which is 9 degrees. So this is going to be one turn. Current is 1.2 amps. Area we found to be 4.33 times 10 to the minus 3. Magnetic field is 0.8 Tesla. And then we have a sine of 90 degrees. Sine of 90 is 1. So this is equal to 4.16 times 10 to the minus 3 Newton meters. So that is the magnitude of the maximum torque on this loop, 4.16 times 10 to the minus 3 Newton meters. Question is, which way is it going to turn? Well, the magnetic moment, which is in the same direction as the area vector, is going to want to align itself with the field. So with the moment sticking out of the page, this thing is going to turn, at least as you're looking at it from the top, like this, so that the magnetic moment can align itself with the magnetic field. So our turn is going to be counterclockwise as you look at it from the top. So that's our answer. Counterclockwise as you look at it from the top view.